Hello, this is Professor Dan Kernler of Elgin Community College back again with another video in my statistics series. This one I'm going to talk about hypothesis testing about means. Okay, let's get started. We've already done some hypothesis testing. If you recall, we looked at the proportion of eligible voters who were registered. We had the general population, and that proportion was about 70%. And then we also looked at our Children of Immigrants database. I'll put that link in the description. And we found that it was 77% of those who were eligible who had registered to vote. Now, these are examples of proportions. What if instead of looking at proportions, we looked at something like average family size? There's kind of this perception that immigrants who come tend to have larger families when they are here. So what if we had this database and we used the database to try to answer that question? According to the US Census, the average number of children per family is 1.86. In our Children of Immigrants database, we don't have average number of children, but we do have average number of siblings of the individual. So we could then add 1 and get the average number of children. So it's actually about 2.80. So certainly at the sample level, it looks much larger, but we know we can introduce more rigor than that, and we'll do a hypothesis test to see if this is actually significantly higher. What we're doing here is we're not comparing proportions, we're comparing means. So we're doing a hypothesis test about a mean. Let's go through our hypothesis testing process. We want to define a null and alternative hypothesis. We want to determine a level of significance, that's the alpha, compute a test statistic, get the p-value or the critical value depending on the method. We want to make a decision to reject or not reject, and then we will state a conclusion. So let's look at ours. Define the null and alternative hypotheses. Well, the null hypothesis, we're going to look at number of siblings. So the null hypothesis, will that be on average, there is 0.86 siblings on average. Seems kind of weird to have 0.86 of a sibling, but you know what I mean. This is an average. Some will be only children. Some will have 2 or 3 or only 1. So this is on average. You'll have 0.86 siblings. And we're doing siblings again because that's what we have in our Children of Immigrants database. So that is going to be our null hypothesis. The alternative hypothesis, again, there's this perception that Children of Immigrants, there will be more, that immigrants will tend to have larger family sizes. And we did see that certainly at the sample level. But remember, there's a variety of options that could happen here. You could think, hey, I think the mean is larger than the original one, or maybe I think it's less than the original one, or I'm not sure, it could be either one, so I'm just going to put not equal to. In our case, we had this question, it was based on the perception, this perception of larger families. So that's what we're going to do for ours, is we're going to use the alternative claim that the mean will be greater than that 0.86. For the level of significance, let's continue with our practice of using 0.05, a pretty typical one. For the test statistic, we're going to use technology, but let's talk about what it's doing. And to do that, we have to kind of refresh our mind about how the sample means are distributed. And we said they were approximately normal with this mean and standard deviation if the sample size was large or X was normally distributed. The problem is we don't usually know the population standard deviation. Like, we have our summary about our data of the Children of Immigrants, but we don't know what the actual standard deviation is for the Children of Immigrants. I don't know what the standard deviation is for number of siblings for the whole population either. So we're going to have to substitute our sample standard deviation. The problem is then that's not exactly the standard deviation of X bar, it's actually the sample standard deviation of X bar. If we look at our Z, our usual Z we're used to, X minus mu over sigma, we can do this for X bar minus the mean of all the sample means over the standard deviation of all the sample means. But if we replace that sigma with S, which would be S over the square root of N, that would be the sample standard deviation, then it's not a Z anymore, it's a T. So we're going to have this T test statistic. So our test statistic is going to be X bar minus mu divided by S over square root of N. And then to get the p-value, we can compute that with a calculator, or we're going to use Statcrunch for that. Let's talk about how to do this test in Statcrunch. We're going to go stat, we want T stats, and then we'll do with data here. We're going to choose number of siblings, and we're going to do the mean. The null hypothesis was 0.86, and we want to do greater than. Remember, that was our alternative, and then we'll hit compute. So our T, very large, 46.25. Our p-value, very small, less than 1/10,000th. For the critical value, I want to talk a little bit about this just for those who might need this. My students, I'm not going to ask this of you, but I should include it. Maybe you might need it in the future. The critical value here, it's going to be a t. The problem is the t depends on n. So if we have a sample size of 50, the distribution might look something like this, where your t 0.05, you find 0.05 area to the right, it's about 1.68. But if the sample size is smaller, there's more uncertainty. And so now you get a t 1.73. If you get an n is 10, now t sub 0.05 is 1.83. So it depends on this sample size, and it's this degrees of freedom idea. We've talked briefly about this before. Let me just refresh your mind about roughly what degrees of freedom means. So let's pretend we have 3 girls and we have 3 lollipops. So the first girl has 3 lollipops to choose from. She can choose 1. Second girl has 2 to choose from, so she can choose 1. But then the last girl, there's no freedom for her to choose. She has to pick that third one. So while we had a sample size of 3, there were only 2 degrees of freedom. So that's kind of a very casual way to think about degrees of freedom. It's 1 less in this case than our sample size. So to get that critical value, we're going to go into Statcrunch, and what we'll do here is we'll go under the T calculator. So stat calculators T. And we want to put in the degrees of freedom. Now we know from our output previously that we have 5,200. 5,200 is our degrees of freedom. We want to find the area to the right. Ignore the results right here. We want to put 0.05 as the area to the right. And then we get our results, that 1.645. Now you might recognize this T 1.645. Like, isn't that just the Z? Isn't that same as the Z? And yes, as the sample size increases, the t distribution becomes very similar to the normal distribution. So when you have a super large sample size like this, there's really no difference between the z and the t. But we do want to get in the habit of using the t here because if we had a smaller sample size, then it would be different. It would be more relevant. Let's continue on in the hypothesis testing process here. We need to make our decision. Well, our p-value here is clearly very small, so we should reject. If we look at the position of our critical value, that's 1.645, and then way over on the other side is our 46.25. So clearly, we're going to reject the null hypothesis. And then when we make our conclusion, I even put here, there is ample evidence at the 0.05 level of significance that children of immigrants have more siblings on average than the general population. So at least based on the database that we have here, it does look like immigrant families tend to be larger than those who are not immigrants. All right, that is it for this video. I hope you found it helpful. If you're interested in seeing more of these, I have a few more about hypothesis testing coming up. You can subscribe, hit the bell to get notified when those come out. As always, thank you to the Elgin Community College Board of Trustees for approving my sabbatical during the spring of 2021 semester. That's the only way I have enough time to record and edit and produce all of these and share them with you. So thank you so much for watching. I really appreciate it, and I will see you in the next one.